So, we'll take another half-half lecture on general issues related to hypothesis testing. Sometimes we are explicitly talking about the alternative hypothesis. I didn't use that word before the break. And so in a way, what we implied in our line of thinking, in what we did before the break, was that the alternative to the null was that the mean was different from the hypothesized value. Now I'm just making it explicit here by naming the alternative hypothesis. And this kind of non-directional alternative hypothesis is basically what we will work with in our course. It is also by far the most commonly encountered type of alternative hypothesis in science and business and society. However, it is not the only possible type of alternative hypothesis. And if you look at old material, we made a little change of direction here in our course over time. Previously, we talked more about those other settings here, because there could be situations where the alternative would be not non-directional, but directional like this. It does exist. It also exists in R. There are even more complicated ways of talking about hypothesis testing, which, for instance, is used by the biopharmaceutical industry. If they, in the biopharmaceutical industry, are going to prove to FDA that they have a new drug which is equivalent to an existing drug, sometimes they must prove that. If it's going to be an alternative to another drug, you might want to be able to prove that it's equivalent only. Not to prove it better or something, just to prove that it has the same effect as an existing drug. That is called bioequivalence. And in those settings, they have their minds on proving that things are the same. So in a way, their purpose of what they are doing in that context is the opposite of the classical scientific reasoning, where we are looking for differences and effects, and we would like to prove that the null of nothing is wrong, that I have something, right? That's the classical paradigm. And by all what you see in the newspaper, most of it, that would be the paradigm lying behind what you read. But other paradigms exist. I just want to make that note here. But you would have to learn those other paradigms later in your life. We stick to the most commonly used paradigm of hypothesis testing, like this. And here the very general definition of hypothesis test that covers what I just taught you, and that covers all the hypothesis tests that will come in the rest of this course and the rest of your life. It consists of following steps. Hypotheses are formulated, and risk level is chosen or decided or put into a contract. It's kind of a contract. If you're a researcher, it's a contract between you and the world. If you're in business, there are explicit contracts between the supplier and the recipient about services that you do, that we agree about the risk level that we are using. And then that's what we are working with. So it's a like contract-based thing that it's being fixed, the alpha level. We calculate, using the data, the value of some test statistic, very generically spoken. The test statistic is measuring the difference between data and hypothesis. Then we have two ways to finish the business. We have the p-value way, or we have the critical value way. And we have seen how they are linked to each other. In the p-value way, with the proper distribution going with the setting we have seen now, a T version, we'll see other versions later, we find the probability of seeing something even more extreme using the right probability distribution, that's the p-value. If the p-value is smaller than alpha, we reject. If not, we do not reject. Sometimes we call that accept, with a warning about the word accept in this context, right? Or we already just check the critical values for what we compute, because we know the distribution before we make the experiment. It's already there, so we can check what are the limits of acceptance and rejection. And if we see an extreme discrepancy, we reject. If we don't, we accept. So two similar ways to finish the story. Personally, I like to do both in a way. Personally, I like that we compute the confidence interval, because the latter thing here is basically like looking at the confidence interval. And it's also nice to have the p-value. So p-value and confidence interval. That's my advice to you. If I should choose one, if I'm being hit with a gun to my head and say, for the rest of your life, you will never be able to use the other method. Choose which one you will go with for the rest of your life. I have no doubts. I go for confidence interval. Don't worry about p-values then. If I were going to make the choice, confidence interval, right? If I don't have the gun to my head, I'll use both. And here the same whole t-test procedure is put. It's basically the same as you already saw. The only new thing is that we explicitly show you the alternative, and we have the finishing of the hypothesis test procedure in this particular context. You can choose between the p-value or the critical value to finish the story. Of course, if the exercise is to find the p-value, you would have to find the p-value. But generally speaking, you could reject or accept based on either approach. I have actually mentioned this risk level way of thinking about the alpha already. You can do two kinds of errors when you do hypothesis testing. We'll get back to this. This is difficult for most people. This is what made Daniel Kahneman do all his nice scientific work that made him get the Nobel Prize in economics, even though he was a psychologist. Because he was intrigued by the difficulty of these probability way of reasoning, that even his very skilled and highly professional colleagues and himself, this is this type fast and slow thinking, right? The fast thinking is challenged here. The slow thinker needs to come in here. The brain needs to work a little here. If we're just using our intuitive fast thinking, we will not do good here. It's difficult without the slow minds in the back. Now, the good news. Let's look at this one, actually, and then I'll get back. The good news is there are two errors to make, but you only make one at a time. That's the good news. You cannot make both errors at the same time. So, phew, that's good. What do I mean by these two errors? Yeah, if we make this, we have this black-white approach for the world for a while. Then there are only two possible options ahead of us. Either the null is true or the null is false. That's the only two options facing us, right? We have to make a decision about what we believe in. So we can choose either to believe in the alternative, that means reject the null, or not reject the null, sometimes called acceptance. Then this is a 2-by-2 table of situations. Either we did a correct rejection, or we did a correct non-rejection, or we did a mistake of one of the two kinds. We might just have rejected the null, even though it was actually true, because there is a risk that I get an extreme discrepancy between the data and the null just by chance. What is the chance? It's 5%, because that's where I set the limit, right? So the risk of making this type of error in this procedure is 5%. We control that risk. It's called a type 1 risk. It's called type 1 risk, and that is being controlled by the level alpha. That's where we start, to control the type 1 risk. We are not going to claim that we found the new cancer treatment if we are not pretty sure that it's okay. So we put that at a low number, right? We must have some pretty strong evidence before we move forward with something, right? So that's why we put it as low as 5%. 10% is pretty unlikely, but it's not enough. I want to be more sure that I found something, so I go down to 5%. And maybe even sometimes further down if I want to be even more strict on that risk. However, the bad news is we can do the other error also, right? We could fail to reject, that is, accept the null, even though we should have rejected it. Maybe the cancer treatment does work better. Just by chance, we didn't see it, we didn't realize it. That type of error is called a type 2 error. I mean, it's not just, it's globally named for those errors in type 1 and type 2 errors. And globally named also the letter beta. Beta is used for many things, but it's also used for this error in this context. This is a difficult one, right? Because this is the one which is relevant. Each time there is a big survey and you don't find anything, right? I didn't find anything. Well, what do you know then? I don't know. Or it's also very easy to make sure that you don't find anything. I just make a sufficiently small experiment. Let me just sample 2 persons, and then I cannot prove the null wrong and the null must be right, because I didn't find that the null was wrong, so it must be right, because I only measured 2 numbers, right? That's the risky part of it. This type 2 risk is then pretty high for such small experiments. Small experiments have high type 2 risks. It's a little complicated concept. We're going to get strongly back to it next week, where we are going to use this approach to think in advance about how large studies we need to have achieved sufficient power, which is the same as 1 minus the type 2 risk. Sufficiently small type 2 risk for having an experiment, a study worthwhile even doing. We'll get back to that. The analogy, court of law analogy. You are accused. A man is accused in a court of law. If we want to take the analogy here, the null is that he is not guilty, that he is innocent. The court of law would like to provide evidence that he's guilty, right? But that you cannot prove him guilty is not the same that you have proved him innocent, but by our principles of laws and most of the world, we wouldn't judge you if we're not certain about that you did what you did, right? But again, not rejecting is in its own right not a real proof of nothing is there. It could just be that you didn't manage to find it because your study was not very good, right? So in the long run, 5% of the time, we might claim we found something even though it's not there. This one is more difficult. Sometimes this is much too big for meaningful conclusions. We'll get back. 2 kinds of errors in hypothesis testing. Let's see. P-value. Find a true statement. Well, you are not doing too bad, actually. Sometimes I made a question like this just by hand raising at just 5 minutes before the ending of the last lecture, and I've seen worse percentages than this. So you're doing pretty well. All right, good. But maybe you're doing different now in a few weeks from now. We'll see there. Good job, Pineapple.